On March 25, 1915, the United States Navy submarine F-4 began a routine training dive. She was operating off the entrance to Honolulu Harbor, Hawaii. The morning was clear, and the sea condition was favorable for the planned training run. The commanding officer took the vessel down for a short, submerged interval to test the battery propulsion and the maneuvering planes. On the surface, the support tender noted the time and waited for the inevitable surfacing broach that would mark the end of the exercise. The minutes accumulated into an hour. The scheduled surfacing window opened and then closed without a ripple on the water. The sea gave nothing back, no ripple, no foam, just an empty horizon. This was the first era of submarine operations where the machines were still experimental and the rules of safety were written in pencil rather than ink. The F-class vessels were small and primitive by modern standards. They were tight iron tubes packed with lead, acid batteries, and diesel engines. When they slipped beneath the waves, they severed all contact with the world above. There was no sonar to track them and no underwater telephone to ask for a status report. A submerged submarine was simply gone until it chose to return. When the F-4 failed to return, the silence on the surface shifted from irritation to alarm. The initial response was a visual search. Lookouts scanned the water for the periscope feather or the white foam of a hull breaching the surface. They looked for the distress buoys that a trapped crew might release. They saw nothing. The Pacific Ocean is vast and deep, and a submarine that does not wish to be found is the hardest object on Earth to locate. But a submarine that cannot return is not hiding, it is waiting. By the afternoon, the reality had settled in. The F-4 was on the bottom. The question was not if she was lost, but where she was lying and whether any of the 21 men on board were still alive. The Navy began a systematic search operation using one of the few practical methods available for finding an invisible object on the sea floor. The technique was known as sweeping. It was a crude and physical process that relied on geometry rather than electronics. 2 surface tugs steamed in a parallel formation several hundred yards apart. Between them, they dragged a heavy wire cable weighted to sink to the bottom. The cable formed a giant loop that scraped across the sand and coral of the ocean floor. The tugs moved slowly to keep the tension steady. The crews watched the wire for the telltale jerk or resistance that would indicate a snag. In practice, it was brutal work. The wire snagged on coral, rock, and old debris, and every catch had to be checked. When the line bit, the tugs had to back and work the loop to learn what held it. Down there, they were feeling the seabed through a single taut strand of steel. The search grid expanded outward from the last known position of the submarine. The searchers worked with a sense of desperate urgency because they knew the oxygen supply inside the hull was finite. If the crew was trapped in an air pocket, they were breathing a limited resource that was being converted to carbon dioxide with every exhalation. After hours of dragging, the heavy wire finally caught fast on a massive obstruction. The location was roughly 1.5 miles from the harbor entrance. The resistance on the line was solid and heavy. It did not feel like a rock formation or a shifting sandbar. It felt like dead weight. The tugs maneuvered to pinpoint the location and pulled the wire tight to center their position directly over the snag. They had found F-4. The discovery brought a momentary sense of relief that was immediately crushed by the second piece of data. The searchers measured the amount of wire paid out and calculated the angle of the hang. They dropped sounding lead lines to confirm the distance from the surface to the bottom. The numbers were checked and rechecked because they seemed impossible. The sounding lines did not stop at 100 feet or 200 feet. They continued down into the dark water until they went slack at a little over 300 feet, about 51 fathoms. The relief on the surface evaporated. In 1915, Navy divers rarely worked anywhere near a little over 300 feet, and the idea of sending a man down sounded like madness. The Navy had located the missing submarine, but they had found it in water that felt, to everyone topside, like the edge of the reachable world. At that depth, the ocean changes the rules. Pressure drives up the partial pressures of the gases a diver breathes, until ordinary air turns hazardous. Oxygen can slide toward toxicity, and nitrogen can narcotize the mind in the dark. This narcotic effect is called nitrogen narcosis. It strikes without warning and degrades the mental faculties of a diver until he behaves as if he is severely intoxicated. A man working at this depth might forget his mission, or ignore his safety limits, or simply drift away into the gloom. If he survives the narcosis and attempts to return to the surface, he faces the barrier of decompression. The nitrogen dissolved in his tissues under pressure must be released slowly. A rapid ascent causes the gas to bubble out of solution like a shaken soda bottle, causing the condition known as the bends. In 1915, there were no proven decompression schedules for work at around 300 feet. Nothing battle-tested, nothing the medical officers could truly trust. The Navy engineers on the surface did not initially send men into this hostile zone. They attempted to solve the problem with brute force from above. The F-4 was flooded and heavy. In her waterlogged state, she represented roughly 260 tons of dead weight. The negative buoyancy of steel plus the water trapped inside the hull. The plan was a vertical deadlift using the buoyancy of the scows and mechanical winches. The engines of the scows roared and the lines pulled tight. For a moment, the submarine seemed to answer, a reluctant movement off the seabed. But the load was ugly and unforgiving. With the wreck far below and the surface never perfectly still, the strain shifted, the rigging chafed, and the lift refused to stay clean. Under shock loads, the lines could part or slip, turning hope into another failure. The failure of the mud scows proved that standard salvage methods were useless against such extreme dead weight at such extreme depth. The cables could not hold the load without damaging the fragile hull they were trying to save. The engineers realized they could not simply grab the submarine and pull. They needed a more sophisticated interface between the lifting force and the wrecked vessel. They needed to attach chains to specific hardpoints on the submarine that could bear the strain, but finding those points and securing those chains required eyes and hands on the bottom. This conclusion forced a terrifying decision. The machines on the surface could not do the work alone. They required human intervention to rig the lift. The Navy had to send divers down to the submarine. They had to send men into the crushing pressure of 304 feet, where the nitrogen would cloud their minds and the decompression debt would accumulate with every second they stayed on the bottom. The physics of the ocean had defeated the ships. Now the operation would depend on the physiology of the divers. Standard procedure was over. Nothing on hand at the station was truly built for this job at this depth, not without unacceptable risk to the wreck and to the men. The geometry was awkward, the waterlogged hull was brutally heavy, and the open swell punished every line. If they were going to bring F-4 home, they would need special gear designed for the vertical physics of the deep. The solution came from the mind of naval constructor Julius Furer. He looked at the problem and discarded the fantasy of a clean pull from a heaving surface. What he proposed was controlled buoyancy underwater. 6 heavy steel salvage pontoons built to take pressure, take strain, and lift straight. They were designed so the lifting chains could run through reinforced openings in the pontoons, keeping the pull centered and reducing the chance of a wild, off-axis slip. Once the pontoons were rigged on the chains, high-pressure air could be sent down to drive out the water inside. As the water was forced out, buoyancy returned, and with it, a steady upward force directly over the attachment points. The naval station in Honolulu transformed into an industrial hub, but the work was split between shores. Some fittings and improvisations were fabricated locally under relentless pressure. The special salvage pontoons themselves were built on the U.S. West Coast and shipped across the Pacific. When they arrived, the harbor became a staging ground where steel, air, chain, and manpower were welded into one purpose: lift. The logic of the windlass pontoons was elegant and irrefutable. They solved the problem of surface swell because the lift would be generated underwater. They solved the problem of cable chafing because the hawse pipes protected the chains and kept the load centered. But the machines had one critical dependency. The pontoons were useless unless the lifting chains were securely attached to the submarine on the bottom. The steel cylinders could provide the muscle, but they could not tie the knots. In the end, the dependency was human. The chains still had to be walked under the hull, around shafts and posts, by a diver on the bottom. The steel could supply the lift, but it could not make that connection. Every descent into the deep ocean casts a shadow of risk that no amount of engineering can fully eliminate. The calculations for the windlass pontoons were perfect, but the variables of the underwater environment were chaotic and cruel. The divers were not just mechanics, they were test subjects in a physiological experiment that had never been run before. They were working at the absolute edge of survival, where a single tangled line or a momentary lapse in concentration could turn a routine task into a fatality. The ocean was waiting for a mistake. On a critical dive to secure the lifting hawsers, Chief Gunner's mate William Lockman descended to the wreck. He made his inspection and started back up. And that is when the ocean turned the rigging into a trap. At about 250 feet, his lifeline and air hose became fouled by the hawser. He was left hanging in the water column, unable to ascend and unable to descend, pinned by a snarl of line that no one on the surface could see. At that depth, the clock is the enemy. Every minute meant more gas load in the body and less margin for error. The tender's topside could not simply haul him clear. A hard pull could tear loose his air supply or tighten the foul into something worse. In the dark water below, Lockman waited, alive, trapped, and running out of time. The team on the surface faced a nightmare scenario. They had a man trapped in the lethal zone, and the only way to save him was to send another man into the same trap. Chief Gunner's mate Frank Crilly volunteered for the dive. He understood the physics of the situation perfectly. He knew that the longer he stayed down to help Lockman, the more likely he was to succumb to the narcosis himself or suffer a catastrophic injury during the ascent. He accepted the probability of death and stepped off the deck. Crilly dropped through the water column and located his trapped shipmate. The scene he found was desperate. Lockman was barely responsive, and the wire was fouled in a complex snarl. Crilly went to work. He had to fight the mental fog of the nitrogen which tried to slow his reactions and dull his focus. He used his hands and his tools to pry the steel strands apart while maintaining his own stability in the current. It was a slow and agonizing process of untying a knot that was tightened by the weight of the ocean. The rescue evolved into a marathon of endurance. Frank Crilly remained in the water for a total duration of 2 hours, 11 minutes. In the context of diving physiology in 1915, this time was almost incomprehensible. When he finally freed Lockman, the return could not be rushed. The ascent had to be controlled, slow enough to keep survival from turning into another casualty. They broke the surface alive, but the cost was visible. Lockman was suffering from shock and the effects of the pressure and required months of recovery. Crilly was physically depleted, but he had succeeded where the logic of safety said he should have failed. His actions earned him the Medal of Honor and proved that a trained diver could function under extreme pressure if he kept his head. The crisis had passed and the price had been paid. The cables were clear and the chains were finally locked in place. The divers had done their part, and now it was time for the machines to finish the job. The salvage operation now shifted from a pure vertical struggle to a complex trap of geometry. The engineers could not simply hoist F-4 to the surface in one continuous motion. A submarine suspended on long rigging in deep water behaves like a massive pendulum. If the surface craft moved too fast, drag on the submerged hull could build sway that snapped connections. If the sea turned rough, shock loads could tear the whole plan apart. So they fought the ocean in increments. Lift just enough to break the bottom's grip, swing her a few degrees, creep her a few dozen feet toward shore. Then stop, reset, and do it again. The work became a grinding sequence of short victories and sudden setbacks. Wire worn down by swell, gear punished by weather, progress measured in feet instead of miles. By late spring, they had managed to bring the wreck into much shallower water, close enough to think the worst was behind them. And then the sea demanded another price. A diver's inspection reported severe damage and a hole in the hull. One more brute lift could have broken the submarine apart. The logic of the operation had to change. That was the pivot, back to purpose-built buoyancy. Chains were rove under the hull at selected hard points. The 6 salvage pontoons were rigged overhead, and high-pressure air drove the water out. The lift came on as buoyancy, controlled, shared across the array, and kept centered as the strain was managed. It was still the step lift, but refined, a geometric staircase built out of chain, steel, and patience. Each step brought the vessel out of the darkness of the deep zone and into the green water of the shallows. 5 months of relentless work had brought them here, begun in March and stretched through the long summer of 1915. They nursed the wreck up from 304 feet to 200, then into the relative safety of the harbor channel, always fighting weather windows, fatigue, and gear on the edge. The final leg would be the most delicate. The pontoon array had to carry the submarine directly into the naval dry dock. On August 29th, the operation reached its physical climax. The special pontoons held F-4 in their grip as the Navy finally brought the submarine up and under control. From there, the wreck was taken in and prepared for the dock, the final methodical step where water could be drained away and steel could be examined. In the days that followed, inside the dry dock, pumps lowered the basin inch by inch. For the first time in half a year, the battered shape of the hull emerged into air and sunlight, no longer a rumor under black water, but an object on blocks, ready for answers. The recovery was a complete technical success. The Navy had retrieved a lost warship from a depth that every expert had declared impossible. They had invented new machinery and new diving techniques to achieve the goal. But as the engineers walked out onto the wet floor of the dry dock, they were not there to celebrate the engineering victory. They were there to perform a forensic autopsy. The submarine was back in United States custody, but the secret of her destruction was still locked inside the flooded compartments. The physical battle against the ocean was over, but the investigation into the cause was just beginning. The water was gone, leaving F-4 as a motionless steel cadaver on the blocks. The naval constructors approached the hull not as salvors, but as coroners. They needed to understand why a functional warship had suddenly decided to die on a calm morning in March. They stripped away the marine growth and the mud to inspect the plating, searching for any sign of collision or a hard blow. But what they were hunting for was smaller than an impact, a weakness that could grow in silence until the ocean found it. The investigation turned toward the battery spaces. In this generation of submarines, submerged power came from massive lead-acid cells, sulfuric acid sealed inside a steel world. The initiating failure was never proved beyond doubt. But the investigating board's best conclusion pointed to corrosion and leakage around the battery tank and its lead lining, allowing seawater to seep into a place that could not tolerate it. If salt water reaches a lead-acid battery installation, the chemistry can turn hostile. Noxious gases can be generated. In a sealed pressure hull, even a short exposure can overwhelm men before they can fight their way through procedure. At the same time, flooding in the forward spaces would drag the boat out of trim. Buoyancy becomes math, and math becomes destiny. Once enough water is inside, the submarine does not choose to rise. It becomes a falling object. There were other theories too. Problems with valves and air lines in the ballast system that may have slowed the boat's ability to blow and recover. But whichever chain of failure came first, the end state was brutally clear. F-4 sank beyond her intended limits, down toward roughly 300 feet of water. Pressure did what pressure always does. It found every seam, every rivet line, every compromised boundary, and it forced the forward compartments to give way. The submarine hit the bottom, and the event was over. The entire sequence, from the first unseen compromise to the final impact, may have taken only a few minutes. The recovery teams moved through the interior to retrieve the 21 men who had vanished 5 months earlier. What they found was grim and quiet. Some men were discovered grouped in the afterspaces, sealed behind a closed hatch, a detail that suggested the disaster unfolded fast, pushing them toward the last pockets of hope rather than giving them time for any organized escape. The tragedy was absolute, but the recovery ended the argument that F-4 had simply vanished. The hull had been brought back. The Navy could study what it could prove, correct what it could correct, and carry the lessons forward. The loss of F-4 forced changes across the force, not just in steel, but in standards. Battery installations, inspection routines, and design details that invited corrosion and leakage were treated as threats, not inconveniences. Existing boats were checked and future boats were built with the lesson burned in. The power that moves a submarine cannot be allowed to poison it. The F-class itself would not last long in frontline service, but the safety discipline sharpened in the aftermath became part of what modern submarining is. The salvage of F-4 stands as a landmark in maritime history. It was one of the most ambitious, deep recoveries of its era, and it set a precedent for what a Navy could attempt when a wreck lay beyond ordinary reach. It proved that the ocean floor was not a sanctuary for lost ships, not when steel, planning, and courage refused to let go. The men of F-4 were lost, but the lessons taken from their recovered hull helped shape safer practice for those who followed. The operation began as a desperate search in open sea and ended with a quiet revolution in the dry dock.